don't have to. Odd, if you remember, or even. This has nothing to do with numbers 1, 3, 5, 11. And this has nothing to do with numbers 2, 4, 10, 12. No. A function is called odd if it is symmetric with respect to the origin. This is an odd function, like y equals x cubed. It's an odd function. It's symmetric with respect to the origin. So if I draw a line through the origin, this piece equals this piece. If that happens, the function is odd, and it's symmetric with respect to the origin. And it's very easy to show that f of negative x equals the opposite of f of x. So this point is x, f of x, and this point is negative x and f of negative x. These two numbers are opposites of each other. F of negative x is the opposite of f of x. A function is even if it is symmetric with respect to the y-axis. Like y equals x squared. So it's called even and symmetric with respect to the y-axis. And of course, the relationship is even easier. It's this. They are the same. One of them is the same, and the other one is the opposite. For our function that we looked at, it was f of x, x to the third minus 27x. And we have to determine f of negative x in both situations. So if I replace x by negative x, this stays or changes into negative x cubed. This one changes into positive 27x, which will equal this. So if I multiply both sides of this equation by negative 1, this is exactly what I get. So that's why the function is odd, symmetric with respect to the origin. Is it? Yes. See, these are exactly the same. In other words, negative 3, 54, positive 3, negative 54. So the entire graph is symmetric with respect to the origin. So the function is odd. Useful to know. Okay, any questions? What I would like to do now is just look at some examples. Let's see, where is my book? My book is here. No, that's not what I wanted. I want here. Before we choose another example and to work to graph, now we are ready to graph. We have all the information we needed. I would like us to choose a problem from 29 to 38. This just solidifies our understanding of the table. Will anyone choose, or I will?
Can you choose?
Which one?
No, can you choose?
Yes, I will choose 37. And we're on page 5. Okay, so f prime of 0 is 0. F double prime of 0 is less than 0. F of 0 is 5. F prime of 2 is 0. The second derivative at 2 is greater than 0. F of 2 is 2. F prime of 4 is 0. F double prime of 4 is less than 0. And f of 4 is 3. I need to make sure that I copied everything, because sometimes I copy from two different problems. My computer is so far away. Okay, f prime of 0 is 0, yes. The second derivative less than 0, yes. F of 0 is 5, f prime of 2 is 0, f double prime of 2 is positive, f of 2 is 2, f prime of 4 is 0, correct. F double prime of 4 is less than 0, and f of 4 is 3. Okay, fine. What is this? I have no idea. Gibberish. I don't understand any of that. Doesn't mean anything. Okay. We have to make sense of this. I have no idea what that means. And I'm not kidding. I'm not just saying that. We just picked the problem. I picked the problem. I have no idea what that means. So step by step, we will clarify everything. So f prime of 0 is 0 means the derivative at a value is 0, meaning this is a critical number for the function. So at 0, f prime is 0. So this must be a critical number, and this is done. F of 0 is 5. Fine. Done. The second derivative at 0 is negative. Done. F of 2 is 2. Done. F of 4 is 3. F of 4 is 3. Done. F prime of 2 is 0. That's another critical number. Done. The second derivative at 2 is positive. Done. F prime of 4 is 0. Okay, that's another critical number. Done. The second derivative at 4 is negative. Done. Okay, now let's analyze what we see. If this is a critical number, oh, one more thing. The second derivative negative does not hold water. Function does not hold water. Second derivative positive, the function holds water. And second derivative negative, the function does not. Okay. At this point, 0, 5, the function has a critical number, and the function opens downward. What type of critical number, what type of extrema will 0, 5 be?
Downward.
Yes, but what type of extrema? Is it a max? Is it a min?
It's a max.
Exactly. This must be a relative max. If it's not a relative max, then the function cannot do this. Awesome. This is another critical number, and the function looks like this, according to the second derivative. What type of point is 2, 2?
Minimum.
Yes. Awesome. Finally, 4, 3.
Maximum.
Yes. You understand that this is extremely clear now, and that is gibberish. I hope you understand that this cannot work. Looking at this, I would have never known how to graph anything, but now I know exactly what to graph. I will plot the points first. What points? 0, 5, 2, 2, 4, 3. So 1, 2, 3, 4, 5, 2, 2, and 4, 3. Good. The function opens downward. It has a maximum at 0, 5. Awesome. the function comes to a relative minimum, 2, 2. It has to have an inflection point somewhere. I don't know where you want to consider it. It doesn't matter. It has to change concavity from opening downward to opening upward. It has to have a point. I don't know where it is, and it doesn't matter. And then it has to change concavity again somewhere because it comes to a relative max and does this. Opening down to this point, which is a relative max, opening up to the relative minimum. So these have to be inflection points. It must be an IP here, it must be an IP here. You can say, well, maybe I want to make it undefined. You can. You can put a vertical asymptote and do something else. But that was my choice. My choice was to show an inflection point. Down, up, down. There are multiple correct answers here. This is one of them. This establishes the importance, basically, of the table. Okay, now let's look at another graph. So now we can choose another function. To graph from scratch, finding everything about the function from the first derivative, everything about the function from the second derivative, and present the graph. If you don't want to choose, I will. Anyone? Okay, I will choose. I want to choose still a polynomial function, or we can choose something else. Let's look at 17. It's a different one. So we have f of x equals natural log of x squared plus 9. Okay, so let's see what happens with this. Okay, I get my table going right away. F prime of x, f of x, and the second derivative.
I think it was a of x.
Yeah, that's fine.
Same thing. Okay.
If you want to call it a of x, that's fine too. Good. So anyone can give us the domain of this function. Do you remember how to find the domain of natural log? What should this quantity be? Anyone remembers the domain of natural log? What should this quantity be for log to exist? Anyone? Do we remember how to find the domain of natural log from chapter 2? This is very important because a problem like this with a domain will be on the next test. What did we say?
Real numbers?
Yes, but what type of numbers should these be? This is not a function defined on all real numbers in general. It could be, but it's by chance. So the functions with restrictions are, number one, rational. So for f of x equals 1 over x minus 1, what do I have to write for the function to exist?
Does that have to be greater than 0? Is that what it is?
No. Yes, for that one, yes. X squared plus 9 has to be greater than 0, correct. But since I'm here and I would like to review this with you quickly. So what do I have to write for this function to exist? Anyone, please? This is from algebra. This is not even calculus.
X cannot equal 1.
Yes, x minus 1 cannot equal 0, so x cannot equal 1. Awesome. Number 2, a radical. Let's say if we have f of x is the square root of 2x minus 3, what do I have to write for this function to exist?
2x minus 3 is greater than or equal to 0.
Perfect. And we have to solve that as x greater than or equal to 3/2. Brilliant. Thank you. And the last one is this log function. So for example, natural log of x plus 3 for f of x equals natural log of x plus 3. What do I have to write? And these are the only functions we have to worry about in this class.
X plus 3 greater than 0.
Exactly. So this is greater than or equal to, this is simply greater than, and this cannot equal 0 in the denominator. Awesome. And well, it happens that this is always positive. Positive, because it's x squared plus 9, it's always positive. So it happens at this point for this function. It's awesome. I don't have any restrictions because this is always positive. 0 has to be in the table, always, unless the function is not defined there. And even then, we have to put it in. So when I plug in 0, then I have to determine natural log 9 right here. So quickly, natural log 9, I have no idea what it is, 2.2. Okay. So now we have to determine these limits because we need to know where the function is going. Let's say you don't remember the graph. If you don't remember the graph of natural log, you have to plug it in the graphing calculator. So let's say we forgot. We forgot how to graph natural log. That's okay. So we're going to go to the graphing calculator, and I'm going to plug in natural log of x squared plus 9. And just plug in huge positive numbers and huge negative numbers because I need those limits. So I'm going to plug in 10,000 or whatever that is, and negative 10,000 or 10 million or whatever is the zeros I got. Okay, so see what happens? These numbers increase. So I can go even more than that. I don't know what the calculator will say. It may scream at me, but let's see what happens. Okay, so it's slowly going higher and higher and higher. So these are infinities. Okay. We also need to set this equal to 0 to find x-intercepts. So when I do that, natural log of x squared plus 9 equals 0. Anyone remembers how to change this into an exponential equation, keeping in mind that this is e? How do I change this log equation into an exponential one? And remember, it goes counterclockwise.